Hello and welcome to the world of NDE 4.0. My name is Johannes Rana, and today is a great day because today I'm finally getting back to ultrasonic testing. Now, I guess you saw that during the last weeks there wasn't really any video about ultrasonic testing, and yeah, I was pretty busy in helping organizing the first international conference on NDE 4.0, which was really successful. And we will repeat that conference actually in April 2022. So if you're interested out there, please join us for that conference. But now let's get back to ultrasonic testing and to the video I promised to you quite a while ago. Ultrasonic calibration and sizing using DGS or AVG. DGS, that's distance gain size. AVG, that's Amplitude Verstärkung Größe. Now, I already did a video on ultrasonic sizing, on the basics of ultrasonic sizing. And I will put a link to that video right here. And in the next about 2 minutes, I will kind of get very shortly back into the basics because we really need that before we get really into DGS. If you have seen that video recently, or if you already know all of that stuff, then just skip it and go right into the DGS stuff. I will put, as usual, a lot of chapter section down here in the description so that you can directly find the section which is most interesting for you. And now let's get started. So, if we are doing an ultrasonic inspection, and let's say we find an indication, we put our probe on the component, we find the indication, we move our probe, and we see that that indication has a certain size. That kind of sizing works only if the indication is larger, and actually pretty much larger, than our beam diameter. And we can use it to get our size in 2 dimensions. Now, what do we do if we have a smaller indication, like this one? Similarly to the other one, we will see it on our A scan. But once we start moving our probe, then we will actually get this kind of shape from our indication, which in reality could look like the one on the right side. Now, how do we get an information on the size from that image? For indications smaller than our beam diameter. Now, there is something called distance amplitude size correlation. So if we think about a component with an indication of a certain sound path, we will get a certain amplitude. If we make that component a little bit shorter, actually that amplitude goes up for the same indication size. And we have kind of a certain relation between our amplitude and our sound path. And if we have a bigger indication, then actually that curve shifts. Now, we can use that concept by using calibration blocks. Calibration blocks with different distances from our surface to the indication and different indication sizes. And we can take those curves and then we can do our measurements. But that takes a lot of time to do that kind of calibration really in a thorough way at the beginning of our inspection, at the end of our inspection, to really make sure we get a good quality. So really from the very first start of ultrasonics, people thought about, okay, how can we make our lives a little bit easier? And there were theoretical approaches using one flat bottom hole. There were theoretical approaches using a back wall. And then there were approaches or there was an approach by the brothers Krautkramer from Germany. And yeah, they kind of combined those two and put it into a neat diagram. So you could imagine such a diagram like the one we used before, doing this over those curves we had before, doing them very accurately, actually already in the factory, and then just actually shifting on one of the, or shifting a little bit on those curves to make them really fit the probe you really have. And this here, that was kind of the first publication on the distance gain size method, or Amplitude Verstärkung Größe. Now let's have a look into a more modern day AVG or DGS diagram, like this one from the so-called B2S probe. What we can see in all those diagrams, on the x-axis, we have our sound path. And if you look onto it, normally we are used to have linear on a linear scale, which goes 10, 20, 30, 40, and then 100, 110. But if we look down here, we can see 10, 100, 1000. And if we look into the ticks in between, we can see, yeah, that first little tick we have here, that is actually 20, then we have 30, 40, and so on. But this one here is not 110. This one is 200, this one is 300. And this one over here, that's already 2000. And that helps to actually have a huge sound path span within one diagram. On the other axis, we have our gain. And then we have a lot of curves which we can see in this diagram. Now, if we look on the topmost curve, that's our so-called backwall curve. Now, a backwall is kind of an indication with an infinite size. That's why this curve is also marked with this infinity symbol. And if we, let's see, go here to about a sound path of 1000 millimeters, we see that we have about 23 dB. And if we go to 2000, we see that we get about 29. And that is a distance of 6 dB. So if we double our sound path on the backwall curve, we have to add 6 dB. That's the slope of the backwall curve. We can already see that the slope of those other curves is steeper. And here, if we double the distance, we have a difference of 12 dB. Now, what are those curves? Those are curves for different equivalent reflector sizes. If you want to say it, those are curves for different flat bottom hole sizes for different sound paths. Now, we already talked about that doubling the distance is adding 12 dB. But if we go here from a 1 millimeter curve to a 2 millimeter curve, so doubling the reflector diameter, here we also have, 12 dB difference. We can also see here, this peak we see here, that's the end of our near field. So this is the near field, and here we are getting into the far field. Now, we talked already about that, yes, we can measure all of those points, but luckily it wasn't necessary for the Krautkramer brothers or for every company to measure all of that. Actually, the points in the far field, you can calculate them pretty easily. Points in the near field, yes, those are the ones you have to measure. So to create such a diagram, you need a mixture of some theoretical calculations and either some simulations or, some experiments. So you are putting a lot of effort you normally do during your daily inspection job. You're putting in the hands of the manufacturer of the probe. And looking into or comparing some DGS inspections with some inspections using calibration blocks. In my experience, DGS is, in a lot of cases, way more accurate. Now, let's see how to use those diagrams. I know those diagrams in the beginning, they look very scary. And I know in the beginning, if you see all of those curves, it's like, oh, what the heck is that? But actually, you will see those diagrams, they are making your life so much easier. Because a calibration is kind of a 5-point process. We start with the usual. We establish, we put our probe on our component. We look for a spot which is without an indication, which is kind of in the middle of the component, and we look for our back wall. Then we adjust our gain so that our back wall actually comes up to 80% screen height. And then we look at our instrument and see, okay, it needs a gain of 14 dB to bring that back wall up to those 80%. And we measure the distance between our probe and the back wall. In this case, let's say it's 800 millimeters. That is actually all what you have to do on your component for calibrating with DGS. Isn't that way simpler than using all of those calibration blocks you need for DAC? Okay, next step is we need our DGS diagram. And it's about 3 steps we have to do on the DGS diagram. So we take the diagram and we are talking about the back wall. So let's have a look on our back wall curve. We know that our sound path is 800. So let's have here a look at 800 millimeters. And what we can see is actually that the gain we are reading from the diagram at this point, that this is actually 21 dB. So what's the difference between the 14 and the 21? Yeah, the 14, that's really our inspection situation with our component, with our probe, with our setup. That diagram is something coming out of calculation. And actually that diagram still needs some kind of shifting, a little bit up or a little bit down. And by comparing those two numbers, or actually taking just the difference between the two, we know how much we have to shift that diagram. Now, shifting the diagram might sound a little bit also something you do not want to do, but you will see how easy it is. So that's about all what we have to do for the calibration. And we now know we have a difference between our diagram and our inspection of 7 dB. Now comes the point we find an indication during, perhaps at that point, that was all the calibration we need to do. Taking 1 point from our back wall, and as the back wall is a large reflector, actually it's really easy to find it, also really easy to maximize it. And taking one look in the diagram and comparing that value we have from our instrument with the value we have from our diagram. That's all. That's the complete calibration. Now we get into an indication. We can use the diagram also for the sizing. So we can evaluate how big is our indication. Now for sure, if we find an indication, we first have to maximize it. We adjust our gain once more to bring that indication up to 80% screen height. We measure the sound path to the indication. Let's say in this case it's 600 millimeters. Yeah. And we can read from our instrument that it takes 66 dB to bring the indication up to 80% screen height. So let's have another look into the diagram. So what we have to do, we take those 66 dB and we add those 7 dBs of difference. We actually we calculated in our calibration process. And with that number, we go into our diagram. So what we do, we look here for a sound path of 600 millimeters. And then we look here for 73 dB. So we look at that exact location. And we see that the curve which runs through that point is the 1.5 millimeter curve. So we know that the equivalent reflector size of the indication we found is a 1.5 millimeter flat bottom hole, or a number 4 flat bottom hole for our American friends. And that's it. We have sized the indication. It was about 3 steps for calibration. It was about 3 steps for indication sizing. The only thing is you should also need that diagram. It saves so much time using DGS. And actually, some of the UT instruments have already the DGS, such DGS diagrams, implemented into the instrument, so that you don't even have to do that work anymore. So, this shows us that with DGS, similar to DAC, we can actually also size indications which are clearly smaller than a beam diameter. Now, there is also a lower limit for DGS and also for DAC, and in some future video, I will get into that lower limit. Now, we can, and that, sizing is done based on the amplitude and the size correlation with the help of such a DGS diagram. Now, such a DGS diagram can also be used not only for sizing indications and calibration, but we can also actually determine the sensitivity. But that is a topic for a different video. So, thanks a lot for watching. If you have any comments, if you have any questions, feel free to write them down here in the comment section. And next time, we will get into sensitivity determination, both with DGS and with DAC. And I think on the video once later, then we will get into, okay, what are the limits of both DGS and DAC? As usual, you will find more information in the description. I hope you like this video. I hope you subscribe to this channel. I hope you give me a lot of thumbs up. I hope I will see you soon. So thank you for watching. See you soon. Thank you and bye.